Hello and welcome to this talk about modernizing J2EE with Quarkus. First, a little bit about ourselves speaking here today.
Hi, I'm Persson and I work as an architect, designer and developer focused on Java backend. As a consultant, I have had the privilege to work with both smaller and larger companies for more than 20 years.
And my name is Björn and I have a background as a developer, but recently I've moved on to mostly work as a solution architect and what I would like to call a container platform plumber. I've been working with Java and integration as a consultant for more than 7 years. And now we'll go through briefly the agenda for today's talk.
I will start by telling a little bit about the challenges with older platforms. Then I will take some real-life examples about modernization patterns, and finally I will talk a little bit about how we can simplify future version upgrades.
And then I will move on to discuss what kind of requirements you can have on modern platforms, and then move on to a quick introduction about the Quarkus platform, and then we'll do a quick demo case about Quarkus.
Even if many older systems do their job, there are a number of challenges with older systems. Some common challenges are license costs, where you can evaluate if you can migrate to cheaper products like JBoss or Postgres. I will not talk more about that, but if you are in this situation, there may be money to save. Another challenge is maintainability, where, for example, older versions of frameworks may cause time-consuming troubles to solve. This may be both costly and affect time to market. It may also be hard to find competence for older platforms. It may also have a negative impact on operation. Scalability, availability, and performance may be a problem in some organizations. Finding competence may also be a problem. If it had not been for the corona, I would like to hear about your challenges as well, but at least you can think about them yourself. You probably have a picture of the beautiful future architecture in your organization. You hopefully also have a picture of the existing systems. The challenge is often to find the roadmap from today's systems to the future architecture. Normally, the transition has to be made at the same time as the systems deliver new value to the organization. This means that it's important to be able to deliver value to the organization early in the roadmap. Value may be different in different businesses. What is value in your organization? The roadmap also has to be possible to perform in a technical way, and it should not add unnecessary extra work. This means that every step in the roadmap should have a purpose and deliver value. On the other hand, every intermediate state of the systems doesn't have to be architecturally beautiful. You need to be pragmatic, but you should have a plan for it. On the next slides, I will show some real-life examples what I mean with this. The first example is an old payment platform that did its job well. We needed part of the payment information for a number of analyses. The solution was to publish all payments as events on a Kafka topic in a common information model. As the payment platform was too old to talk to Kafka directly, it posted the payments to a REST service that publishes to the Kafka topic. This is actually an example of an architecturally good solution with good decoupling. It's easy to add new listeners, and that has been done in this case. The second example is an example of a programmatic solution. We had an old master information system, it did its job, but no one had changed it for many years and no one wanted to take the risk. We needed information for a high volume and rich of Kafka events. There was no service returning the requested data, and even if it had been, the performance was not good enough. The solution was to periodically fetch information directly from the database and update a Kafka state store. The Kafka state store was used to the enrich operation. This solution is not what you would find in an architectural best practice book. It is a pragmatic solution that delivers value to a small cost. As the data model has not been changed for more than 10 years, it's likely that this solution will work until the master information system is replaced. We had an old system called by sending binary buffers to MQ. The response came on MQ as well. We needed to call it from a client only talking REST. We also needed to translate a key by looking it up in another system. The The solution was to create a facade service, calling the two services and making all technical stuff with binary buffers and MQ. The REST service interface is done according to the future architecture and may remain unchanged when the old system is replaced. The last example is about an old integration platform that did its job well. It handled a lot of unrelated areas. It was time-consuming to maintain and change. In some areas, we also needed token-based security, which this integration platform did not support. When there was a large change in one area, we created a new integration microservice for that area. We also tried to get the clients to use the new services. When all clients in an area had moved to the new services, we removed the old ones. This was a stepwise move toward the future architecture. It's easy to introduce and deploy, as old and new services may live in parallel for a while. After some years, most areas have moved out of the integration platform. So how do we simplify lifecycle management, like Java updates and introducing new versions of frameworks in new systems we build? Normally, the updates are easy done, but the problem is time-consuming manual regression testing. This makes the developer think, I do not risk breaking anything by introducing a new version, even if it would simplify my current task. Newer frameworks make it possible to start a full version of the system with an in-memory database, an in-memory messaging system, and so on, when performing the JUnit tests. This makes it possible to test each scenario automatically end-to-end, including security and configuration. The JUnit tests actually perform a REST call to the service actually stores information in the database, and so on. This is a help for the developer during development and maintenance, but it also helps during refactoring and performance updates. All regression tests are done in minutes and finds unwanted side effects before the code is even checked in. And it's also a help when lifting Java version or versions of frameworks. You start by lifting the version or versions, then you run the regression tests, and that is done in minutes instead of days if it had been manual testing. You then fix possible problems and rerun the tests. When the tests are greens, the update is done. We have found that this way of working makes version updates a side effect of other development tasks. It normally only takes minutes. In contrast, updating a system with manual regression testing may be a full project. This is not a help for already existing systems without tests, but is something I would like to recommend when you build your new systems to be able to perform better and faster version updates in the future. Thank you.
Okay, so we just heard Anders talk about different ways of going about modernizations, going into some real-life examples about modernization patterns. But now the question is, how do we actually implement those modernization patterns? And what kind of technology platform should we select? I will now introduce the Quarkus Platform for those that haven't already heard about it. But in short, it's a modern and flexible microservice platform, which is meant to be container native. And you can use it to easily interoperate with, adapt or replace old systems while still using modern technology. But let us zoom out for a little bit and look at the bigger picture. What kind of requirements do you have on a modern platform in your organization? Of course, it will be very different depending on where you're coming from and what kind of competence you have focused on. But I will go through what I think are some base requirements when selecting a modern platform. I think it should be runnable on some kind of container platform. And why is that, you might ask? But I think a key thing is that you get homogeneous deployment of your applications, so they all deploy the same way. It's also very easy to provision up new environments. For example, if you want to spin up a test environment for a new project, or scaling quickly in production to some new feature you want to launch. There are also many operations benefits, for example, availability of the platform, and it's also quite some nice tools to do rolling deployments to reduce downtime during a deployment. You can also get some quite nice benefits with effective resource use, where you have your container orchestrator that distributes your loads across a set of hardware. So those are some key base requirements. But then, depending on your organization, you probably have a lot of other requirements, like it should integrate with this and this system, it should run with this pipeline, build pipeline. And then you can have some more niche requirements that I think also a lot of modern platforms can fulfill. For example, high scalability, if you want to scale to handle a really high load in production. Or you might require elastic scaling, that you can scale your load, your deployments with the load that's coming in. So for example, at peak, you run 20 instances of your service, while in the night you might only run 5. And that could save you some money, for example, when running in the public cloud. And if we step back a little bit more to see what kind of journey are we looking at here when moving from older platforms to modern platforms? Well, one recurring theme is more like a philosophical way of looking at your services. You might have heard people talking about pets versus cattle. So typically your older systems would, in this analogy, be more like pets. You care very specifically about the system, it has a name, it has to run it in its certain habitat with all these little helpers and scripts to keep it going. While in the more modern view of these modern platforms and microservices, you tend to view your systems more as cattle. You don't care about a specific instance. You care that they are easy to replace. For example, this is what enables you to do these rolling deployments and just throw away the older instance, bring up a new one, and have it run quickly and flexibly with some new configuration or just maybe using more resources or some other configuration change. But if we then get into Quarkus, what is it for those who haven't heard about it? Well, if you read on the website, it says that the tagline is a Kubernetes native Java stack. And it also says that they have a high focus on a low memory footprint and a fast startup times. The project is quite new. It was started by Red Hat in 2018, but it's still been developing at a pretty rapid pace for being this new and had a lot of new features and improvements during that time. But what is it exactly then? Well, it is a Java framework and runtime, similar in scope to Spring Boot. Of course, the ecosystem is not as large as Spring Boot or Spring, which has been around for a long time, but it's still pretty big. But one of the key features of Quarkus is the focus on supporting Graal VM-based ahead-of-time compilation. So Graal VM is a project out of Oracle that allows you to, instead of compiling your Java code to this bytecode that can run on any platform, you compile it specifically to a binary that can run on a specific platform. And why do you want to do that? Well, it's because of these gains you get from that allows you to have a lower memory usage and maybe a fast startup time. Is that important for you? I should say also all Quarkus applications can run the normal way without doing this ahead of time compilations. And there are different pros and cons to selecting either way. But if we move out to the technical specifics and instead look at more the developer experience. So Quarkus allows you to do both a more typical traditional imperative programming style, but also supports the reactive paradigm and this more asynchronous way of thinking about your program. It also has great support for different kinds of standards and libraries like CDI for dependency injection, JAX-RS for REST services, and different kinds of standards and libraries. For example, Camel if you're doing a lot of integration work. There are also a lot of modern conveniences for you as a developer, a very quick live reload feature, and this kind of simple configuration mechanism that you typically find in other modern platforms, such as Spring Boot. If we move on to look at the specifics about the memory and startup times. So here is a performance diagram taken from the Quarkus website. And here they've compared Quarkus running in two different configurations, the ahead of time compiled one and the JVM normal one, to a more traditional cloud native Java stack running on the JVM. And this, I believe the cloud native stack they're comparing to is this Thorntail project. But I think you can think about it as a Spring Boot similar thing. But of course, if you're concerned about comparing to specific alternatives, you should do your own evaluation to see what kind of numbers you get for the scenarios you want to compare for. But I think this can be pretty representative. So what we see here is that for this REST example project, even running Quarkus on the JVM saves you about half of the memory footprint. And if you instead move to the GraalVM based ahead of time compilation, you're almost at 1/10 of the memory consumption of this traditional cloud native stack. And if you look at an example with REST and CRUD, for example, with persistence, the differences are not as huge, but they are still pretty significant. And if we instead move on to look at the response time, so this is the boot of the application to the first response time of a REST call, you can see there are already pretty big differences comparing the traditional cloud native stack to Quarkus on the JVM. And if you look at the ahead of time compiled version, it's really, really quick. So this allows you, for example, to run these kind of serverless applications where you have this scale to 0 on the first request you start up your application. And it also allows you to quickly scale elastically if there's a cluster of requests coming in at the same time. You might want to scale up your service very quickly to meet that demand. But I encourage you to do your own testing to find out if this is the kind of gains you can see for your own application and domain. So now we'll actually go into the meat of this part, which is a Quarkus demo based on a case which has this kind of theme of modernization with older systems in mind. So let's imagine we have this old product master data system, which might be a little bit slow to serve requests. It might be hard to change. And then you get some new requirements. You want to serve a high volume of requests with low latency. So in this scenario, we'll imagine a Quarkus microservice to implement a cache to solve this problem. And if we look at this little diagram I drew here, you will find it's very similar to one that Anders showed before. So we have this old system exporting data through a REST call with a little adapter so that it ends up on a Kafka topic. And then we'll consume from that topic in our new Quarkus microservice to implement this cache. So let's go into the demo. So here we have the implementation of our product data cache in Quarkus. So this might look familiar to you if you would worked with frameworks such as Spring Boot or something with JAX-RS annotations. It's a similar principle. So we have our class here, and we have some annotations to denote how it actually exposes the REST endpoints. So here we have something at the base path of product. We're going to serve JSON to the client. And here is our specific REST endpoint. So you can query it with a GET operation with a specific product ID as a path parameter. This maps to an argument in this method. And we use this product ID to do the lookup in a cache. The cache is simply a concurrent hash map, mapping an integer to a product object. So looking at the definition of the product object, it only has a few fields: the product ID, name of the product, and the category. And this is pretty standard. We just look up the key in the hash map. We get the product, we check if it's a match, we do some logging. If there's no match, we throw this exception, which would give us the 404 HTTP error. So pretty standard for an HTTP operation. And the interesting part is perhaps how all of this links into Kafka. And here we're using something called microprofile reactive messaging and a specific connector implementation called smallRye Kafka. But basically how we use this is that we have an annotation here to say that this should consume from the products channel. And then we have our method that takes then a product, and what we do with it, we do some logging, and we then put it simply in the cache. And we'll look into a little bit how all of this is wired together with the configuration. But all in all, it's a pretty simple, fits on one screen, but still implements our kind of caching behavior and consuming from Kafka. So let's have a little look at the configuration here. So basically, we say where the Kafka server is at. We specify what kind of reactive messaging connector we're going to use. And then we have to specify this deserializer class, which I will mention later as well, to say how we're going to deserialize messages on the Kafka topic. And here we map this reactive messaging channel to a specific Kafka topic with the name products. They happen to be called the same. We have some options for exposing a Swagger UI for a REST endpoint, which we'll use to actually do some testing. And this part here is then a bit unfortunate, but so GraalVM is a pretty new project, and it has kind of a bit of complexity in that it has to be able to compile for different platforms such as Mac OS X, which I'm on now, which apparently is a little bug around. But I think it's more stable for compiling to Linux, which is what you typically would do if you do some kind of Docker image build of your application. Anyway, it still works to compile a native image, as I will show you a bit later. And just having a quick look at this deserializer class here. It's pretty just some boilerplate, and you might think, why do I actually need this? Can't this be inferred? Maybe there is some optional plugin to kind of generate this one, but the base difference here to more traditional Java frameworks is with GraalVM, to build this kind of binary, you cannot rely as much on reflection, or at least not in the same way without some configuration options. So you have to be more explicit about what classes you are going to use and how you're going to use them. This is my understanding at least. But this is not too hard to implement. We simply point out the data model class here and do a boilerplate implementation of some class here. So this is basically it, and we'll move on to a little bit of testing of this. I've included here a Docker Compose file that allows us to easily bring up a one-node Kafka cluster to test with. And we're going to be sending in two different kinds of messages here. One with just product ID 1, toothpaste, in the category of hygiene. And then we have a simple update of this data here, where we change the name to strawberry toothpaste. So I have TV-checked the setup a little bit. Here we have my Docker Compose running Zookeeper and Kafka. Here I have a console which would allow us to... I wrote a little wrapper script to be able to send these messages using some Kafka CLI tools. And we'll just simply send in this JSON file. And here we'll start up our service. And now we're going to use the Maven Quarkus plugin, which allows us to do this live reload mode. We're not going to get into it, but this is typically how you would start it in your developing process. So we see it starts pretty quickly. It writes some things about the communication with Kafka, and we will send a message here. And I can tell you that since this is using some Java tooling behind the scenes, it actually takes a second or something to start up the JVM. And this is the kind of a startup time you can avoid with Quarkus and doing ahead of time compilation. So we see that it logged down here that it updated the product cache for this product. And if we then instead move on to look at the Swagger interface here, we're gonna be able to see our service, hopefully. Yes, we can. So here is the generated Swagger UI for this REST endpoint. We see our product endpoint here, and we can try it out then. Put in a number, product ID 1, we execute it, and we get this content we sent in with the initial toothpaste name. We'll just send a quick update here with a second version. Takes about a second to start everything up there. We can also see our query log here, and that we both did the query, and now we update it again. We will look at the update quickly here. So now it updated to strawberry toothpaste. So we have our microservice implemented. It was pretty smooth running. I will just show you briefly. I'm not going to show the compilation of the ahead of time binary, but I have done it here before. So we have both our typical jar, which is the normal thing you're building with Maven and Java application, but this here is another binary built with Graal VM. And I'm just gonna show you quickly how fast it is at starting up. Very quick, and maybe you won't be even able to tell the difference, but if we're gonna start up the jar instead, it takes, well, maybe, I don't know, 100 milliseconds extra at least, maybe half a second. So I encourage you to experiment with this yourself and look at the memory consumption and everything, but I think it's a pretty nice framework and allows you to write pretty concise implementations. So I think that was it for the demo. We'll just sum up with some final words here to recap the presentation. So Anders was talking about a lot of real-world examples of modernization patterns. And I think the key take-home message there is to be pragmatic about your modernization steps and have a clear roadmap what you want to achieve. And when you're evaluating what new technological platform to use, you should clearly evaluate your requirements against what's out there. And I would say you should strongly consider Quarkus as a platform for implementing such modernization patterns and other services in your organization. So thank you for listening to this talk, and I hope it was interesting for you.